yeah, there. I see what you mean now. All right, how's that? Falls over. Okay.
You started recording?
It's recording right now. Yeah. Hopefully. All right, so we were looking at number 5. So the first question said that B was a subset of C. So that means, is every element of B also an element of C? So is that true or false?
False. Oh, wait.
True, right? So every element in B is also in C.
Yeah.
Okay. Now B says that C is equal to the set AB. C is equal to the set A union B, right? But this is saying that C contains the elements capital A and capital B. C does not have the elements capital A and capital B, and it doesn't. So this is false. Now again, if you wanted to correct this, you could say C is equal to A union B. That would be correct. So if you were to union A and B, you would get C. Make sense? All right. C says that the empty set is not a subset of A. Say that again. Oh. Is not a subset of A. So is that true or false? False, because every element of the empty set is also in A, isn't it? And that's the definition of a subset. So if you pulled everything that's in the empty set, all of those things are in A. So this is false. In fact, the empty set is a subset of any set. So we could call X. Right? The empty set is always one of the subsets. If you were to list all the subsets, the empty set is always one of them. And then D said that the complement of C is 3, 4, 6, 7, 8. So what does complement mean?
Everything except, well, everything, the universal set minus what's in the set.
Right, so the universal set is 1 through 8. Let's take out a 1, a 2, and a 5, and that's what you're left with, right? So this one is definitely true. So your question is going to be similar to that. The idea is just to know about sets and set notation, okay? Be careful, one of the other ones that we do in 230 all the time is we'll do something like this. This is saying that the empty set is an element of something.
Is it?
The empty set's not an, well, the empty set is a set.
Like it can
Right.
be, it can be an element, but it has to be.
But then, yeah, he would literally have to be like inside.
Yeah.
So if this was A, then this would be true.
Yeah.
But this would also be, well, both of these would be true if that was the set.
Yeah.
Okay, the empty set is a subset because the empty set is a subset, but it's also an element because it's actually in the set. Okay? But the only way for the empty set to be an element of something is for there to be an empty box in your box. Okay? Does that make sense? So the curlies mean you have a box. Anyway, so that's what your number 5 is going to be, a true-false kind of thing involving sets. Okay? You can probably pull out your 230 book if you still have it and look through those, because that's probably where I took them. So, that's number 2. Number 3 wants you to draw a Venn diagram. So that was like number 7. Just make sure that you label it so that I can see what you are shading in your final product. This was number 2 on exam 1, and all the pieces in there. So the video was so I think you guys all did okay with the Venn diagram. Okay, well, so we'll look at it real quick. So this one we had A complement, union, B take away C. So make sure you start with a universe. The universe is super important, especially if you have to complement something, you usually need the whole universe, right? So if you don't put that box around it, you're gonna have a problem doing complements. And then with three things, just put three guys in here. Make sure that they have their three intersections and the one triple intersection. And then make sure you label it. I'm gonna call him A, him B, and him C. And so it says that I want to union. Unions are nice because that means whatever you shade, you're never gonna have to take away, right? Because it's union. So I know that everything in A complement is gonna be in my final answer. So I'm just gonna go ahead and shade A complement horribly. Okay, so there's my A complement. That is everything that's not in A. And then what I want to do is join on. Oh, actually, I do remember grading this one. There were a few problems here. So I'm unioning that. This is B take away C. That starts with B. So here's B. And I want to take C out of it. Okay, so just looking at that part. So B, the set of everything B, take away C. Looks like that. That is B, take away C. So what am I adding in? I'm adding in this part right here. That part was already there, but if you want to shade the whole thing, you can. So this is B, take away C. I'm unioning that with A complement. So there's three parts that are not shaded. That's it. In the whole, we're done. In the whole thing, this part of A, this part of A, and this part of A are not shaded. And so when I was like assigning point values, I was like, oh, so 1 point for this, one. I pretty much gave a point for each piece. And then I did 2 for the universe. Just because I figured everyone would draw a rectangle. So everybody gets 2 points. So just be careful there. If this had been intersection, then you would just want to know what the two had in common. And so that would have just been this top part of B, right? So imagine this picture again, with this part shaded and then that part shaded. The only thing they had in common was that yellow area. Also, I just noticed that I used this notation on the exam, but that C means complement as well, so those would be the same thing. Now, if there's any in between the ones we're doing that you're looking at your test and you want to see me do, just call it. Or that you want to do yourself. And let's see, number 4 is a one-to-one onto or surjective injective type question. Like number 8. And that one, actually I did this in class, didn't I, afterwards? Because it went a little kinky on your guys' exams. For some reason I thought I had. So let's look at this one though. This is looking at whether or not a function is one-to-one or onto. So think back to your 230 days. We actually had to prove these things in 230. But also, if it's not, then all you need is an example of why it's not, okay? But in order to answer these questions, you have to know what they mean. So one-to-one, by definition, means that if A1 is not equal to A2, then f of A1 is not equal to f of A2. Okay, so that's the actual definition. So if A sub 1, oh sorry, I should write it, we're doing a function from, we'll say it's A to B. So if A sub 1 is equal to A sub 2, then f of A sub 1 is equal to f of A sub 2 for all A sub I, whatever, in A. Well, I guess I gotta put both of them. this is what it means to be one-to-one. It means if you plug in, again, the contrapositive is so much, oh, guys, I said it out loud for some. If you plug in two different things, you better get two different answers. That's what this says. Now, normally we use the contrapositive though, because it's the same thing, right? Contrapositive, logically equivalent. So normally we say if f of a1 equals f of a2, then a1 equals a2. So normally this is the way we write it, for proving purposes. So looking at the function that we were given in number 8, we have g from the real numbers to the real numbers, defined by g of x equals x cubed minus 3. So if you're looking at it and you really don't think it's one-to-one, then just do an example. Be like, look, if I plug in a 2, I get 3. If I plug in a 4, I get 3. And 2 and 4 are not the same number. You see, if you plug in two different numbers, you're supposed to get two different answers. So if you can come up with two different numbers that give you the same answer, then we have a problem, okay? This one, however, is one-to-one. So here's how we will show that it's one-to-one. The contrapositive is very easy to work with. So you would just say assume, or let, whatever, assume f of a1 equals f of a2, or we can just do a and b. Oh, it's g, sorry. Assume g of a equals g of b, and this is for a and b real numbers. Well then, what does that mean? Well, it means, I'm just plugging in a. It means that a cubed minus 3 is equal to b cubed minus 3, which implies that a cubed equals b cubed. And I always just think to myself, let's solve for a. If you solved this for a, what would you get? You'd get b, right? Because you'd get the cube root of b cubed, which is b. Well, according to this, if the y, or if the y values are the same, then the x values have to be the same. So I assumed that they get the same y value and showed that they had to be the same x values. That's it, we're done. Therefore, g is 1-to-1. So we've just shown that g is 1-to-1. If you think back to algebra, that was the horizontal line test we just did. So then it asks about onto. So the definition of onto is that there exists A in A. Wait, I guess do it the other way first. For all B in B, there exists keep putting the words together. There exists an A in A such that f of A equals B. So in other words, you give me any element of the codomain, anything you want, I can find an A that would get you there. That's what it means to be onto. So in modern algebra, you may have said that the codomain is the same as the range. That's what this is saying. The codomain, the set for the codomain is equal to the set for the range. How do I know? Because you give me anything out of the codomain, I can find you an element that got me there. So in other words, it's also in the range. Okay? And vice versa. So first we would just ask ourselves, is it true? If there's something glaringly obvious, then you can just put an example and say it's not onto because 5 is an element of the real numbers, but f of a can't ever equal 5. Like, you see what I mean? But, so does it look like I could get any real number out of this? You could always like, this is what x cubed looks like. It hits everything, doesn't it? So, seems like we're going to be good to go. So now let's show that it's onto. So, just let B be a real number. And define, so see, you're gonna come up with the A that works. So what A could I plug in and it would be equal to B? So in other words, I wanna know what could I plug into this? So G of what would be equal to B? In other words, you're looking for the inverse, right? What would give you a B? It's x cubed minus 3. So what if it equals B, here's our scratch word. I need for this to be equal to B. So in other words, I need this to equal B plus 3. So what do I need this to be? The cube root of that, right? So I'm going to define A equal to the cube root of B plus 3. That's obviously a real number, it doesn't have any problems, right? If it was a square root, we'd have to worry a little bit, because square roots can be imaginary. But this is a cube root, so we know it's a real number. I might even just stick that over here, instead of like trying to overly explain that. I'm just going to define A to be that thing, which we know is a real number. Well then, G of A is equal to G of the cube root of B plus 3. Which is equal to the cube root of B plus 3 to the third. What's our function? Minus 3. Minus 3, which is equal to B plus 3 minus 3, which equals B. So we just found an A that will get us there. We found an A that's in the domain that will get us there. Right. So now, this will work for anything. If you said, oh, but how do I get a 7? I'd say, oh, plug in the cube root of 10. If you said, oh, but how do I get a square root of 2? I'd say, plug in a cube root of 3 plus the square root of 2. You see, so this is giving us, well, it's the inverse. So on your scratch work to the side, you're finding the inverse. And actually, is that part of this question? Why or why not use the definitions? No. The next one said to find the inverse. But you use the inverse to do this one, but technically you don't even know if it has an inverse until you've done both of these things. Because in order to have an inverse, you have to be one-to-one and onto. But that's it. Oh, therefore, G is onto. So we just proved that G is both one-to-one and onto. Therefore, we would know that it has an inverse. Which you don't actually have to find in this one. Let's see if, oh look, the next question says find an inverse. So, are there any questions about this one? But just make sure you're using the definition. Now again, if it was no good, let me just show you real quick what no good would look like. So let's say that instead of x cubed, this was x squared. We're going to have a problem. So first, look at the one-to-one part. The one-to-one thing says if you plug in two different numbers, you better get two different answers. What would happen if I plugged in, oh, I don't know, a 1 and a -1? Wouldn't I get the same answer? So because it's like, oh, wait, that's not one-to-one, you can just show an example. You can just say, notice G of 1 is equal to G of -1. They both happen to be -2. But 1 does not equal -1. So that's using the forwards to disprove. Oh, no, it's not. It's using this one, yeah. So I'm still using the contrapositive, aren't I? So I'm like, hey, look, the y values are the same, but the x values are not. So, not one-to-one. And then you can do the same thing with onto. I think we can see that this is not going to be onto. Give me a real number that you could never get.
A negative number.
Not the way it is,
Oh,
it's got
sorry,
-3. So.
something less than -3.
All right, so
-4.
pick one. -4. So you can just say, notice, -4 is a real number. However, I don't know what's wrong with it. All right. X squared minus 3 cannot equal -4. And then I'm over your shoulder saying, why not? Well, because x squared cannot equal -1. So there's the more obvious part of it, right? And we're done. Because see, in order to be onto anything you pick in the codomain you have to be able to get to it. But there's no way that you can get to a -4. So you're done, and you can just say, so it's not onto. So if it's not, it's a little easier because you just need an example. But you still have to explain your example. You can't just say 1 and -1, and then just move to the next part. You have to explain why that means it's no good. Again, using the definitions. I think everybody got number 9. Did anyone have a problem with number 9? I think I was going to take off a point for notation if you didn't write F inverse with a little -1, but I don't know if I did or not. So number 5 on the final, you're going to have to find the inverse. And you'll notice that on this number 9, I could have run into real problems if this wasn't x cubed plus 5. X cubed plus 5 kind of looks like this. So regardless of the domain and range, really, it's 1-to-1 and onto. But I really should have put down the domain and codomain on number 9. Because I said if the inverse exists. Well, you don't know if it exists if you don't know the domain and codomain. So I made sure on the final, it's going to give you, it's going to say find the inverse of the function f that goes from here to here. So you're given the domain and range, okay? And then it says to find the inverse, but also what are the inverses domain and range? Do you guys remember how that works? Yeah, you just flip them, right? When you find an inverse, the key step to finding an inverse is swapping everything, right? You interchange the x's and y's. Well, that interchanges all x's and y's. So like if the original had a horizontal asymptote, now you got a vertical. If the original had a hole at 5,3, now it has a hole at 3,5, right? If the original's domain was going from the integers to the real numbers, now you're going from the real numbers to the integers because all the x's and y's get swapped. So that'll be number 5, will be like number 9 on that first example. With the added bit that it gives you a domain and range that you'll have to. So it doesn't even ask if the inverse exists. I'm telling you it does. So find the inverse of this function. What are its domain and range? Okay. Number 6 on the final is using the breadth first search algorithm for weighted graphs to find the shortest path. I made sure that it didn't have to go through a particular place. Notice, okay, so still on exam 1, just real quick. Number 10 is accounting. You're going to see that in chapter 8 stuff. Number 11 is an equivalence relation proof. That's on your take home. Number 12 is an induction proof. That is on your take home. So we can go back over those if you want to on Wednesday. But let's just keep going over. I did mean Wednesday. Yeah, we don't have class Monday. So, but these are going to be, so those last 2 questions are going to be take home, or on your take home final. Not the exact questions, but those types of questions. So really, 1 through 5 are going with exam 1, and then we move on to exam 2. And again, the first one is using the breadth first algorithm. And make sure that you're labeling when I go to grade that one. So on that exam, it was actually 6 points for the labeling, 3 points for the path, and 1 point for the answer. So it was all about the labeling. That's what these algorithms are all about. So now on The exam, I had you go through one of those middle points, which I'm just gonna have you do normal on them. So on the test, you're just gonna start at A and you're gonna fill out the whole graph, and then you'll answer whatever question I asked. Does that make sense? So this one, and some of us did it differently. What I did is I started at A, I made him my 0, and then I worked out from there in both directions. So I found everybody's distance from A, and then just picked the shortest, because whatever point you pick to begin with, when you're done with the labeling, that's everybody's shortest distance to where you started. That's what the breadth first search algorithm does. So whatever point you pick to start at, when you're done with the labeling, the labels show you the shortest path to wherever you started. So I had my starting point as A. That way I could just say, okay, the shortest to S was 4, the shortest to T was 7. So now I know it's 11 total, and here's how I got to each one. Okay. Now, some of you guys ended up with different answers than me, and that's fine. On the final, I made sure that you have to do it the way you have to do it. Right? So why don't we do number 6, but we'll change the directions. We'll just get rid of that vertex part as we do it right now in class. So we're just going to find the shortest path from S to T, period. That way we can practice with the algorithm. Okay, so let's look at number 6. And we are simply going to have S be our starting point, and we're going to label the whole darn thing. Okay, so here's S. So I'm going to start by labeling S. He's going to be my starting point, so I'm going to label him 0, because I haven't done anything yet. And where did I come from? Nowhere. So here's S's label. All right, so now I'm going to label everybody that's near him with their distance from A. So this was a 2, so I'm going to label him 2, and he came from S. I said A, I'm sorry. This has A. So he's 2 from S. He is 1 from S. And this guy is 1 from S. Okay. I remember doing this in like paintbrush and having to move all the numbers over. All right, so now we're going to move out again. So breadth first. First we moved out by 1. Now we're going to move out by 2. And again, we're still trying to find minimum distance. So we're going to look at who would, let's see. So we can look at C now. Oh, I didn't label that top one. Oh, that was the one I labeled with
We chose
a letter.
Yeah.
We chose 1. Okay.
Really made us think of that one.
So now let's label him. He could either come from B, in which case it would be 3, or he could come from E, in which case he would be a 2. So which one do you want to pick, 2 or 3? It's not really a choice. 2? All right. So his distance is 2, and that's coming from E. All else is 2 away? A is 2 away. So looking at A, lots of places he could come from, let's see. He could come from C and be 4. He could come from B and be 4. He could come from E and be 6. Technically, we haven't labeled him yet, but that would be a 5, right? Or technically more than, it'd be a 6. So his shortest, he actually has 4 in 2 different places, but we're going to go alphabetical. So we'll go with B, right? So let's say he's 4 from B. Also, we really want him to be, if this wasn't a labeled graph, a weighted graph, remember you're trying to find shortest, so you would pick the one that's only 2 away. All right, so now for I, so he's 2 away, so he can come from H, in which case he's 3. Again, looking at it the other way, you can tell that that's going to be reasonable. So he's 3 from H. All right, so now let's move out one more. I keep wanting to say degree, but I'm degrees of freedom, like from the guy. All right, so looking at D, I could get there this way, 2 plus 1, that would be 3. I could also do some kind of craziness and come over, but that would be 4, 5, 6, 7, that's way too many. So we're going to get to him, he's going to be 3 coming over from C. All right, F, he can technically come from D, in which case it would be 5. He can come from A, which would also be 5. He could come from I, that would be 7. Or he could come from J, but notice that would be what, 12? That's too many. Now I forgot which one was the shortest. I just said a bunch. A. Oh yeah, so A and D are actually tied, right? So alphabetical. So we'll pick A. So that's going to be 5 from A. So now we're looking at J. You can get to J from I, in which case it would be 11. Or you can get to J from F, and how much would that be? If I got here from F, how far would it be?
6.
It'd just be 6, so let's go with that one. All right, now G. So we could go this way, that would be 6. We could go this way, it'd be 11. We could go this way, it would be 8. So we're going to go 6 from D. And now we're at T. So we can do 9 or 11. Let's go 9. And that came from G. So this is the entire labeling. And wherever you started from, that's what all these labels tell us. So now I could say, hey, Stephen, what's the shortest distance from S to F? Did you see F? What's his label?
F, that's 6. No, wait, no.
It's a 5. You see it?
Oh, now I see it, yeah.
So F has a 5. So I could say, what's the shortest distance from S to D? Kyle, what's the shortest distance from S to D? 3. What's the shortest distance from S to J, Cammy? 6. So see, all of these labels are telling you shortest distance from S because he was my starting point. So again, that's why on my exam, I just said that A was my 0 and I went out from him. That way I could just grab, I just added the S and the T together. But so in this one, if we just shed shortest S to T, then we would say it's 9, and then we would take the path backwards. So he came from G, who came from D, who came from C, who came from E, who came from S. So it would be S, E, C, D, G, T. And so this was where the difference was, I think, on the exam. Like some of you guys did like J to T, and some of you did like JGT. They're both distance 5. so it doesn't really matter which one you would have picked there. But if you, actually, I don't even think I did JT. I think I've got JGT or something on mine. Doing the breadth first, but you get the same distance, right? Whichever one. So on the actual exam, if you had started at A and just gone out from there, your path would have been S, B, A, F, J, G, T. Some of you had just JT, which is fine, because it's the same. So this is the breadth first search algorithm. And so I've got everything labeled. I have my final answer. I did not, oh, why did I put a 9 there? Oh, it is 9. I was thinking it's 11, looking at the test. So labeling, path, answer are going to be your big ones. I'm also going to ask you to color somebody. So that's what chromatic number means, right? That's the minimum number, and we're not edge colors, we're vertex coloring in here. So there's also edge colors. So the chromatic number is the minimum number of colors needed to color the vertices so that no two vertices so that no edge is adjacent to the same two colors. So you should have been able to do this one right here. You can do it in how many colors? 4. You can do it in 4. Make sure you somehow show that to me. Don't just put an answer down. So in that one, these were all worth 10 points, but it was 5 points if you wrote the number 4. And it was 5 points if you had some kind of explanation or like actually colored it. I pointed out that there was a C4 in there. If there's a C4, you're gonna need at least 4, right? You see that box right there? That's a complete graph on, K4. It's a complete graph on 4 vertices. So all the vertices have to be different colors. It's a complete graph, right? So we know that we need at least 4. You can't possibly go less than that. So anyway, however you want to show your work on that, just make sure you do. And I made sure on the final I actually said, find the chromatic number and color it. I put color in quotes. So however you want to color it, you can use different letters. Just make sure you don't use like blue and brown and just put B's down, because I won't be able to tell.
Do we bring crayons?
You can bring crayons, do it. Bring markers. Pretty sure I had somebody last 2 years ago bring their markers in for the fun. Okay, so yeah, so number 7 is going to be like 7. Okay. So 6 is like exam 2, number 6, right? Huh, weird. Okay. And then number 7 on the final will be like that one. And then the next one is depth first search algorithm. So remember, for the depth first one, that one takes less thinking than this one. The breadth first, actually, you have to do a little bit of thinking because you have to do comparisons. With the depth first, you just kind of go, and then when you hit it at dead end, you back up. So it's kind of nice. It's just dive right in. So you had to do that on number 10. So let me just compare the directions. Apply a depth first search algorithm to the following graph to obtain a depth first search numbering of the vertices. Then use this numbering to form the spanning tree that was described in theorem 5.7. I hate when people do stuff like that, theorem 5.7. What the hell is that? I just didn't feel like typing the whole theorem up and everything. But the point was to do the spanning tree. And remember, that theorem is actually kind of an algorithm on how to find the spanning tree. So actually, Stephen, I guess this is another algorithm. So there's the depth first search algorithm, which results in a numbering that you can then use to make a spanning tree. I think you guys did pretty well with that one. Didn't you? Any problems with that one? You want to see that one? All right, so looking at number 10. Again, this is the depth first. This is where you get to just, well, delve in, I guess. And this was a nice one, so it was just to start, I didn't do it. I went ahead and started with A, just because it's an A, it's nice to start with. And it kind of starts the same way as the breadth first, but on the breadth first, the number is telling you the distance, so that's why it starts with a 0. In this case, the number is telling you an order. So when you put things in order, you don't say that this is the 0, 1, right? You start with 1. So I'm going to label A 1, and I'm going to say he didn't come from anywhere. All right, so now what I want to do is move 1 away from him. That's it. And we're going to do it alphabetically. Maybe this is why I messed them all up, just to see if you guys were paying attention. So when there's options on where to go, just go alphabetically. So I'm going to go here. He's going to be labeled a 2, and he came from A. So now I'm going to move 1 away from him to someone who hasn't been used yet. You can't use somebody that's already been labeled, right? So if I were going to move from him, I could either go back to A, but I'm not allowed, or I could go to F, or I could go to G. So which one will I go to? Which one? F. Let's go to F. So this is going to be 3, and that came from C. All right, so here I go again. I've got options, let's see, C, D, G, and H are all of his adjacent guys, but C is already labeled, so I'm not going there. So where are we going to go next? All right, so let's go up here. That's going to be a 4, and it came from F. Okay, now we just keep going. He doesn't have a choice on where to go, right? Those two are already labeled, so we're going to come down here. Oh, we have choices. We can either go to H, because he's not labeled yet, or we can go to E. So which one should we go to, just to keep things alphabetical? In other words, what comes first? Right. So we'll go over to E, so he's going to be 6 now, and that came from B.
On mine, there are edges from E to G and H to B.
What?
2, bottom, diagonal, edges.
Oh. Not on mine. So we did not have a choice there then. So now we're sitting here, and everybody attached to us is already labeled. So are we done? Yeah. So here's where we're just going to back up. So we'll back up to B, and this tells you where to back up to as well. I got stuck here, back up to B. All right, did B have any other choices? No, so I'm going to back up to D. So now I'm at D. Does he have any choices? So I'm going to go back to F. So now I'm here. Does he have any choices? So we're going to come down here and make sure you keep track of the number. What number were we on?
This would be 7.
7. And oh, my fingernail. And he came from F. And oh, only one place to go now. So he's going to be 8, and he came from H. So now the entire thing is labeled with the depth first search algorithm. Sorry, resulting in the depth first search numbering. All right, so now we're going to use that to form a spanning tree as described in theorem 5.7. And how did it actually define it? I mean, we're just grabbing all the edges that we just made. So we should have A to C. We're going to have F, C. Oh wait, what am I going to do? Yeah. Yeah. But I'm at F. Oh, there we go. Thank you. Sorry. All right, then we have this one. I'm just going to go back the way we came. Then we had that one. Then we had this one. Then we went up and got this one. And got this one. I was trying to think of it like the computer would, because the computer will look at the labels. So we need edge EB, BD, DF, CF, HF, GH, CA, and A nothing. And I don't mind if you even scribble on it like that. This is where colors, you can do colors again. You can say the blue is my spanning tree. I agree, Drew. So this one was all about the labels again, so if you're wondering why you got what you got, It was 8 points for the labels, 2 points for the tree. Let's see. Set it in the same graph. It's different, okay. Number 9, you guys did really well with number 13, pre, post, and in. So we're not gonna do this, we don't really have time, but I'll just go ahead and write down. The next one is the pre-order, post-order, in order, okay? And I think, aren't, the graphs I put on this test, weren't those the same ones we had done in class? I can't remember if it was the same graph.
I think they were a little different.
They were a little different, okay. So the ones on the exam are different. And I put circles on the exam instead, that way you could put the numbers in the circles. Yeah, so the vertices are circles on the exam. But it's 3 graphs. Oh, and I can't remember if it was this test that I graded, or maybe I'm thinking back to the one from 2 years ago, but I remember somebody did all their labelings, but they didn't write which one was which. And they were all like out of, and they weren't in the order it was asked for, and so I was like, well crap, how do I know which ones are, but anyway, make sure you write like, this is my pre-order, this is my post-order, this is my in-order. So that's what number 9 on the exam is gonna be. So just make sure you practice those. They can be frustrating sometimes, I think, for me anyway. So we will stop there for today. And you can practice those, you can go back over. I think that when I was grading those last 2 on the first exam, I'm pretty sure I wrote lots of stuff on your guys' papers. So if you can try to, go back over those, see what mistakes you made, because those 2 are gonna be on the take home. And I will give you your take home on Wednesday when I see you next. And then it will be due Wednesday, May 1st. Bye-bye. All of your classmates, say goodbye.
Bye.